And hello, welcome everyone to this video on turbulence modeling. So in the last videos we are talking about lots of wall functions and how they work in OpenFOAM. It's just one example of CFD software. And today I want to move on to something a little more important, practical. I want to talk about how to make your simulation reasonably accurate, and of course accuracy is important for CFD in general, and you always want to compare between CFD, some experiment, or CFD and DNS, direct numerical simulation. So, and of course you want to have you want to have some guidelines on how to define your mesh and all this sort of things. So it's techniques to make the techniques to make the CFD simulation a little bit more reliable. Okay, so these are some guidelines, they're rules of thumb. Of course, if you want to really make it accurate, you have to delve into the theory, but I'll just give you a brief overview. Alright, so these are the references. They call Quasi-DNS capabilities of OpenFOAM for different mesh types, numerical study on turbulent mixed convection using blah blah blah, hybrid RANs, LES, DNS of combined natural and turbulent convection in a vertical plane channel. Of course, Stephen P. Pope's famous book on turbulent flows. Then you have the CFD practical approach by Yeoh and Tu. And new version of detached-eddy simulation. This is the detached DDES model. Spalart's paper, a very interesting look into meshing near the wall, because that's actually what triggers the switch from the RANs model to the LES model. And of course you have spatial resolution requirements for DNS for Rayleigh-Bernard convection. This natural convection is included in this kind. So these are some of the papers I'm using, and I want to cover some cases of convection. Okay, first and foremost is forced convection, or in fact, you can use these guidelines for normal flows as well, because most of these flows, they are pressure driven or they are driven by some free stream velocity. These mean that there's an external driving force that is driving the flow. So these are forced flows. Most flows, if you talk about aerodynamics or anything else, these are forced flows. Anything to do with natural convection would go into the realm of heat transfer already. So these are you don't use exactly the same guidelines for natural or mixed convection, but we'll use forced convection first. We'll talk about forced convection first and use that as sort of a reference to kind of compare like mesh sizes for the different kinds. So firstly, for forced convection, first off, forced convection or forced flow. So this is a forced convection flow, or standard fluid mechanics flow without any kind of heat transfer, scalar transport. By scalar transport, I mean you are transporting temperature or some concentration of a reactant or what have you. Okay, it can be pollution or anything like that as well. But these are very basics. Okay, forced convection or forced flow. This is fluid mechanics only. So the rules are pretty similar. Alright, so first we want to talk about DNS, the most basic. Alright, we want to resolve everything. If we want to resolve everything, we use DNS, right? DNS. There's no model. The Navier-Stokes equations are solved fully, just like in laminar flow, except here you kind of need to take into account this turbulent stuff. So what is the length scale? What is the length scale of the grid? Okay, so the length scale of the grid, these are actually determined by something called Kolmogorov scales. Kolmogorov scales. So it's this Russian mathematician called Kolmogorov. He actually helps to define the scales of turbulent fluid simulation. And Kolmogorov scales, these are actually the name, it's named after him, but in the physical representation or physical meaning is that these are the scales of the smallest eddies. So let's say you have a free shear flow. You have a flow of a fluid in the free shear region. You have a U mean. Okay, you have a mean flow here, and inside here you have, of course, your eddies. You have big eddies, small eddies. And of course, the big eddies are more oddly shaped. The small eddies are usually more isotropic. Okay, I think I want to delete all of this. Okay, let's go with this simple picture first. So you have these big eddies, and then you have these small eddies. Okay, how do we determine Kolmogorov scales? How do we determine Kolmogorov scales? All right. Okay, so this will be our reference length for turbulence in general. It helps us to get a very good insight into why we have such length scales at all. So this is actually done via energy balance. Okay, so how is energy being transported in, let's say, turbulent flow? So we're not going to talk about convection first. We're just going to talk about fluid mechanics in general. So what we have is usually we have some mean flow. All right, we have some mean flow. So remember the mean flow, we have some profile like so. Okay, where this is the velocity, and this is, let's say, the direction x. Okay, across some tube. So the mean flow, okay, will have to dissipate its energy somehow into turbulent kinetic energy. So it's going to transport energy into turbulence, because that's how you have flow like this, and then there's a U mean, and some of that energy is being dissipated into eddies. So we have the largest eddies here, large eddies. Okay, so this is actually, in most of the turbulence classes you would have gone through this, but I'll just go through this again, either as a refresher or just to make sure everyone's at the same page. Okay, so you have turbulence, and then you have some energy transport from the mean flow to the large eddies. What these large eddies do, at very large scales, they are very unstable. Let's say they can wobble around, and they can be very oval shaped, very stretched, and okay, we have a lot of stretching. Okay, they have a lot of stretching, and the thing about, it's just like raindrops. Okay, raindrops or water droplets. Okay, it's a very poorly drawn water droplet. Okay, if you have a big water droplet, okay, if you have a big water droplet here, and what it tends to do is to break up into smaller blobs of water, and after that you keep breaking down these smaller and smaller water droplets, and then eventually you have a shower of so-called rain. If you were to randomly throw a big pot of water or pail of water in like 3,000 meters in the sky, and then you throw it, the chances are it will tend to disperse itself until it becomes like little raindrops, and they are of a certain characteristic size, because viscosity kinds of holds them together at this scale. This is very similar to how an eddy is being dispersed. You have a big eddy, and then the big eddy kind of stretches, it will deform, and it will break up into smaller eddies. So okay, it will break up into smaller eddies. So this is actually very much like you throwing a big pot of water very high in the sky, and then it kind of disperses. It's very similar how an eddy would behave. It will have a big eddy here, and then it will split up, it will stretch, it will elongate, it will split up into smaller eddies. And after that, beyond a certain size, you find that at a very large scales, you will have eddies that can stretch and deform, but when you cut them down to smaller and smaller, they become more and more spherical. Okay, so here you have a very interesting phenomenon happening. So how is energy transported? You have it going from big eddies to smaller eddies in this breakup mechanism. Okay, you have a breakup mechanism. Okay, so this is very much where we have, and of course if you look at the shape, you will find that these are anisotropic in the very big scales, and as you break it up smaller and smaller, they look more and more spherical, very much like water droplets. So these become more and more isotropic. Okay, and in the water droplet case, here we have viscous forces dominating. Viscous forces dominating. Okay, viscous forces dominating, and this is where you have the highest amount of viscous dissipation. Whereas the viscous dissipation here is negligible. Okay, what I'm telling you now, this is actually what we call the energy cascade. Alright, energy cascade. Alright, so you have this picture of turbulence where you go from the mean flow to large eddies, then you have some so-called medium-sized eddies which are smaller. I'm just arbitrarily defining some scales of length here, which there's a lot more detail to it if you want to go and study it. Yeah, so but I won't go to too much detail. I'll just give you a rough idea, Okay, then you have the smaller scales. Which are we call Kolmogorov scales. Okay, so this is the energy cascade, and where does all this go? You have viscous dissipation and you go into heat. That's what the picture looks like. Alright, so this is the energy balance or the energy cascade. It's very fundamental to understanding turbulence. Okay, so consider a rough energy balance of sorts. So what is the rate at which we have our mean flow getting its energy into the large scale eddies? Okay, so we kind of do a scale analysis here. We have the energy from the mean flow going into the large eddies as such. Okay, and we see it cascade down. Okay, cascade down all the way into heat, which is the whole thing about friction. That's how it works. Basically, the idea is that whatever energy I feed in from the mean flow, if you were to draw a box here, the energy I draw in from the mean flow over here is the same as the energy I dissipate into heat. So this is sort of energy balance, and the energy into the turbulence equals to the energy coming out of the turbulence at some kind of a steady state. It looks like a steady state thing, but it's not truly steady state. We call it stationary turbulence, or I don't know, whatever. I'm not going to use the proper terminology here, but the energy you feed into this turbulence cascade is the energy that you draw out. That is the basic assumption and idea. So you want to kind of find the energy that's going in and the energy going out here, and they should be equal. So what's the energy going in over here, right, from the mean flow? So the energy going in, it will scale as, the rate of energy going in rate of energy going in, it will scale as, so I'm going to use this tilde to represent scaling. it will scale as, let's say, some sort of kinetic energy, and then you divide it by time. So this is the rate of so-called kinetic energy being fed into this eddy system or energy cascade as a function of time. So what is this kinetic energy? This kinetic energy, okay, so I'll use a different color here. This kinetic energy, I mean, we like to talk about per unit mass, so it's easier to compare. This kinetic energy usually scales as half u naught squared, okay, or u mean squared. What is this u? This characteristic velocity. This is the large scale characteristic velocity here in the pipe or channel or whatever have you. These are the characteristic velocities. It can be free stream, it can be pipe, whatever. Okay, so this is the sort of the scale of the kinetic energy that's being fed in. Now, of course, I'm only interested in the scale here. This is just a scaling analysis to give you a rough estimate on the order of magnitude. So we usually like to write this. The kinetic energy is some sort of u naught squared. I mean, we take out the half because that's on the order of magnitude of 1 anyhow. So we just want the order of magnitude, so we got u naught squared up. So that's our kinetic energy scale. And what about our time scale? Now, our time scale over here, we like to say it's a length scale over the velocity scale. All right, what's the length scale here? The length scale here is, okay, we can take a look at our definite pipe flow again. The length scale of the largest eddy will be comparable to, let's say, the length scale of the pipe. So the length scale of the largest eddy here, which you can contain, will be comparable to the length scale of the pipe. So it will be on the order of this pipe length scale. So remember, this is from the energy cascade. The where we are feeding in, it is from the mean flow into the largest eddy. So this is the length scale that we use. It will be somewhat characteristic length scale of the system. For example, a pipe or channel width. So if we were to substitute this in, we would just say, okay, I mean, if you want to substitute strictly, we use the half u naught squared, and we have a time scale, which is L naught over u naught, and that, if we take out the half, then we'll be left with this, u naught cubed over L naught. Alright, so this is how the rate of energy transfer into the turbulence cascade. So the rate of energy in will be over here. U naught will scale as u naught. Okay, I'm not gonna write there. It'll scale as u naught cubed over L naught. So that's the energy in. And what is the energy out? It should be the same as the energy in. So we can write this equation. We say that the dissipation rate, we call it epsilon, that will also scale. This is the dissipation rate per unit mass, of course. Okay, it will scale as the kinetic energy over time as well, and it should be equal to u naught cubed over L naught. All right. Okay, so that's step one. So how are we going to use this relationship to help us determine the Kolmogorov length scales? So the trick is this. It is you can get the energy balance here. All right. We can say this: the rate of kinetic energy input. Okay. Rate of kinetic energy input is here. Is equals to the rate of kinetic energy dissipation. And how do we characterize this dissipation rate? So I'm going to say this dissipation rate epsilon, it will scale as some kinetic energy in the Kolmogorov scale, which we will, here we like to use this term eta to represent smaller scales or Kolmogorov scales. So eta. Okay, so this is the typical scale of Kolmogorov, which is we like to use eta to denote it. That's what you find in literature. So when I say The length scale is actually eta. You can write it L eta, or you can just write it simply as eta. This is the Kolmogorov length scale. Okay, and for time scale. So time scale, we like to also write T eta. Okay, so it will be some kinetic energy over some time scale. Okay, this is just for scaling analysis. Okay, I'll continue in the next video. Thanks for watching. I'll see you guys again. Alright, goodbye.